I'm Basil Hosmer. I work for Adobe Systems, and I'm going to talk a little bit about Mesh, which is a programming language project I'm working on. So I guess this is kind of a, hey, look at my language presentation. It definitely has a lot of threads from earlier today.
Okay. So first, a little background. I actually work for the programming language research group at Adobe, which is sort of split between product work, advanced projects, and some research.
Can you speak more loudly?
Sure. I thought I was blowing out the room, actually. Okay. Programming language research group, product work, advanced projects, and research. Mesh is a dual-purpose project. It's intended to be a new thing, clean slate, but also to spin off interesting feature ideas to existing products, and also spin off research topics. The status of Mesh as a project is that it's still very, very much work in progress, development ongoing. The plan is to open source it in its current form by the end of the summer, roughly, and keep working on it out in the open. So this is basically a kind of a preview of the stuff that's interesting so far, but it's not by any means complete. So the design goals for Mesh are basically that it captures some combination of appealing properties from languages that are out there. The first one is that it be a productive and enjoyable development environment. So the idea is that it bridge the gap between languages that focus on the capturing the fun of actually building stuff, but leave in the service of flexibility, leave precision out to some degree, and languages that are very heavy on abstraction design, but which don't necessarily capture flow as you build programs. Part of the brief for Mesh is that human readability and the natural qualities, the human sort of intuitions that apply to working through what a program does are important, that they have sort of pervasive effects on the kinds of programs that get written and so on. It is intended to be a construction kit, so things that look like they can be pulled out and snapped into other places should actually do that. Types, a sophisticated type system is a big part of Mesh, but it's not intended to capture sort of big hierarchies of abstraction. It's intended to capture precise and sort of flexible structural descriptions. And of course, I think any language that is sort of aspiring to be used now needs to come with a much better concurrency story than is currently available in mainstream languages. So here I basically am just trying to draw a picture of that. It's certainly not a unanimous consensus, but the idea here is that functional languages and scripting languages both are sort of attuned to that idea that if you get out of the way and let the developer achieve sort of a state of flow, that is its own reward in some sense, that you should essentially sort of put that at the top of your list of priorities, even if it means certain kinds of things don't get encoded in the program, although clearly functional and scripting languages have their own ideas about what can be dropped. Statically typed languages, the idea basically here is that the type system is a high bandwidth pipeline between you and whatever tools you're using, and that facilitates part of the development process in a way that's basically irreplaceable. That tooling, for instance, is something that can be a participant in a way that's much more substantive if you have static types. And the idea behind imperative languages being part of the mix here is that they have, that some process of natural selection has been applied, and the intuition of the imperative model, first a program does this and then does that and so on, is significant, that it's a way people think about programs. So that's what Mesh starts from, an imperative fairly typical looking syntax and semantics, a bunch of functional power tools. It's mostly immutable. We're going to see a lot of stuff that echoes things that Rich said today and has said in the past. And the control and operations in mesh are all done with combinators and lambdas, but they're done in such a way that they don't, they're intended to sort of harmoniously blend with the way people read programs. That's an important point. And it has a powerful type system, but again, it's intended to capture structures and sort of the interplay of abstract things that values reflect at given moments in time rather than a rigid taxonomy of abstractions. And it has an STM-based concurrency model. So it's already clear that there's, a lot to talk about. It's all kind of entangled. And so rather than just go through a laundry list of features, I'm going to use concurrency as kind of a through line to get, some kind of linearity in this talk. And we'll show a couple of demos and see language features in passing, and then I'll dig way deeper into any of this that anyone is interested in at the workshop later or, whenever. Okay, so just a little preamble about sort of the concurrency problem. This is sort of a well-trodden path at this point that the reason that there's so much less concurrency code than there could be or should be, given the multi-core future we're living in, is because it's too hard to do. That the outcomes when you try and do concurrency are too variable. You might, it might just not work. You may take too long. It may give you like too many bugs. And so unless concurrency is an urgent need for your situation, it's often wise to just not try. So the other thing that I think is important to note, I'm sure it has been noted, but it's not as pervasively talked about, is that concurrency under a current model is something that's sort of the worst lock-in story ever. You have tricky decisions to make. You have to make them right at the beginning of your project, and once they're made, they marble through the code. So basically, you've hit the trifecta. You have to guess at a lot of stuff. You might guess wrong, and then too bad. So it's sort of a, the waterfall model in a way that's, inescapable if you're using traditional sort of setups. And so practically speaking, it's very wise to just not do it if you can avoid it. So the obvious conclusion from that is that any kind of setup which lets you do concurrency in ordinary, non-urgent situations has to be separable. You have to be able to have the code that makes decisions be somewhere else from all the rest of the code, and the rest of the code has to work properly regardless of what kind of concurrency design you've put in place. And that has to happen at design time, certainly, but it also, at compile time, that's the process of dropping in different modules, and at runtime, that's the process of selecting a concurrency strategy depending on what machinery you find when you wake up. So concurrency agnostic, of course, means concurrency safe. So if your concurrency agnostic code has to work everywhere, it just has to be concurrency safe all the time. So it has to be easy. So the pitch is basically that a particular kind of STM lets you address those things in a way that's effective. And I'm not going to just talk through the slide, but basically it has to do with the fact that if you can write it correctly and that correctness is propagated through composition, and you are always writing code that's safe at a low level, then you have the recipe for disentangling your concurrency strategy from the rest of your code base. All right, so what particular flavor of STM is this? Well, it's, That logo down on the lower right is there for a reason. It has actually an interesting history because you have to start with an idea of immutability. And obviously, there's a lot of ways to do it, but the ML setup is nice and intuitive and feels natural. It's basically everything is immutable except for these little containers, which just hold a value at a time, and you can put a different value in it at a different time. MVCC, multi-version concurrency control, has been around for a while, and it you know, is very familiar if you just listen to Rich's talk and his talk from, you know, his closure talk from a few years ago. And it shows up in a few places. It's basically a version history that represents a series of values over time. There was a paper on STM in, I think, 2005, which applied this to STM rather than to databases. And then, of course, it was part of the closure, this sort of inspirational closure setup, which I think really generalized this model. And there's one crucial thing that closure added, which is persistent data structures, because that makes this model scalable. So if you look at like the version boxes paper, they basically are using as examples, in most of the paper anyway, things like doubles, you know, or numbers. So clearly, if you have one of those and you put a new one in, the logic of the time-based indexing and so on works. But you have to be able to scale to big structures, which means copy on write, which means something that spares you from copying big structures around, really. And persistent data structures does that very, very nicely. So that's the foundation that Mesh builds on. And Mesh adds a few things that turn out to be pretty important, at least in certain use cases. One is you get the serializable level of consistency. It's a little bit of sort of transactional inside baseball, I guess. But basically, that's the sort of bank account safe level of consistency, which is more than you need in some cases and more expensive than snapshot isolation, which is consistent but not bank account consistent to sort of informalize it. But Mesh does that just to sort of reduce the API surface and make it foolproof. The other thing, which turns out to be not just useful in certain use cases, but useful in simplifying the mental model of transactions, is that it simplifies and sort of strengthens the guarantees around when a transaction retries, or really when it doesn't retry. So I'm going to move on and we'll get back to that. But the important thing is that it lets you, in situations where you absolutely cannot retry, you can set up your transaction so that it won't. And because Mesh is strongly typed, there's an API which sort of codifies certain patterns of transactions that are simple. One of the things we'll get to is that lots and lots of transactions are really simple, surprisingly simple. And so the strong typing in Mesh lets you exploit that. All right, so here's the mental model. And you know, it's this is a sort of my personal way of thinking about it, which is not nearly as elegant as like Rich's diagram, for instance. But basically, it's the pages flying off the calendar, or you know, a flip book works too. So a box is the place where immutability happens, and it just holds a value at a given instant, and then that value goes away and a new value comes in. So as as program time progresses, the pages fly off the calendar. And the other thing that is worth adding to that mental model is that when a transaction happens, a few things change on a single page, so to speak. So when you compose atomic operations together in a transaction, what you're doing is saying that a given program instant has several changes associated with it, several mutations. So you know, all the values outside boxes are immutable, even the big ones. And all of the changes to boxes are concurrency safe in a low-level way. So basically, what you have to do is write the logic that's correct. So it's a really natural model. I mean, it's a lot like how you kind of, or how I naively thought, when I first heard about threads in general, for the couple of minutes before you're introduced to just how much of a hassle it is to keep things from moving underneath your feet. You think of, some imperative tasks, kind of looking at some shared data and reading it and writing it, and that's pretty much how this model feels. Again, the thing that is very, very hard to sort of imagine before you start writing code this way is how few when you look at transactional papers and stuff, usually the examples, it's often easy to slip into a kind of a misunderstanding that a transaction is sort of like a thread, that you take your code and you stick it in an atomic block and it runs for a while and it's, magic happens so that it's safe. But it's not like that at all. Transactions are like assignments. Transactions, for the most part, are little tiny things. Once in a while, we'll get to a couple of demos that sort of show this to a modest extent. Once in a while, there will be a transaction that has non-trivial logic in it. Most of the time, they're either dead simple updates to single things, or they're synchronized updates to a couple of things at once. All right, so here's some demos. These all use processing, which is a library that has an execution model that's sort of like the thing I drew at the bottom. It, a user-defined draw function gets called back at 60 hertz or something, and so it's very, very amenable to concurrency because it's the most natural thing in the world to put a shared state in the middle of a few threads that are updating it, and then let the draw function just sort of look at what's happening. All right, so this one here, the first demo is just an image browser. It downloads some thumbnails from Flickr based on a tag. You have a contact sheet, you drag it around. When you reveal new spaces, more thumbnails are downloaded in parallel. And then you can click for a full view. So let me tell you a little bit about what's going on beforehand. And we'll dive into the sort of what's going on in more detail in a second. But the basic idea here is you're parallelizing network conversations in a very simple way. You're writing network interactions in synchronous straight line style without callbacks or anything like that. And you're using some reactivity that is based on transactional updates triggering user code. All right, so let's see here. You guys see what's going on? Okay, so the spin means that images are getting downloaded, so it just downloaded that grid of thumbnails in parallel. And if I click on one, it'll download. The window is actually extending down below the level of the screen here. So I'll just drag some more, and basically you can, sort of, as you drag, more thumbnails get downloaded, and so on. And just for fun, also notice the spinner, that little weight cursor thing. That'll come up later. All right, so that's basically it. All right, so let's see if I can get PowerPoint to come back to where I was here. Can everybody hear me okay? Am I dropping out at all? Okay, I'll try and keep it loud. Okay, so again, this is basically the simplest setup for that program you can imagine. There's a little pile of shared stuff in the middle there. The blue stuff is the shared data. There's a map actually of images. There's a position coordinate for where the viewport is, and there's a tag that's a string. And then there's these concurrent processes that inspect and update that stuff without coordinating with each other at all in a very straightforward fashion. So, the viewport looks at where you are and looks at the images. The mouse messes with where you are. The keyboard messes with what you're searching for. The interaction of those will trigger a parallel download of a bunch of thumbnails on occasion, and the clicking on a particular thumbnail will provoke a full-sized image search. So very straightforward. This is basically sort of the action version of that. Revealing some new stuff triggers a download. And here's the thing to picture. While you, the programmer, who are knocking out this app, it's not a super critical concurrency app, but it could benefit from concurrency. This is the point. The mental model there is, I just found out I need to go download some stuff. It would be convenient and fast to do it in the background, certainly, and in parallel, probably. I'll just start up a process that does that and dumps the results into the global resource that everybody's looking at. And that's what you do. So here's some mesh code. I'm not, the particulars of the source we can get into later and in the workshop, but the important thing here is just that it's very straightforward. There's a synchronous conversation with Flickr that gets you a bunch of URLs based on a search tag. And then there's a parallel for loop, so to speak, actually a combinator, that goes through those URLs and runs a synchronous conversation, runs a download, a synchronous download, and then an update for each one. So it's really like not, concurrency management is completely absent from this. In this particular demo, there's really no coordination that goes on either, except for the fact that everybody's sort of working at a central resource. But the point is that lots of programs are like this. And for programs that are like this, using this kind of model is dead easy. So a brief sort of side trip into some basic syntax. This is a let in mesh. It's very simple. The whole language is basically as simple and conventional as possible, given what it's trying to do. So all lets are immutable. They're all strongly typed. The types are all inferred, so annotations are optional. So if we were to sort of query the shell, we'd find that the type of the search function there takes a triple and returns an array of strings, and that the variable is an array of strings. One other side note is that mesh uses a tupled function model. So all functions take a single argument, and the tuple literal syntax is parens and commas. So this thing that we're looking at here is a pass of a triple into a function that takes a single argument. So that turns out to be really useful in this sort of combinatorial Lego game, because it means that things like map and reduce and some other more imperative and friendly looking combinators that mesh uses, you really can throw around argument lists to arbitrarily sort of multi-argument functions without having to do anything special. There's another thing that I hope to get to now, but if not now, later, which is that mesh generalizes over variable width tuples to get things like, the zip function to be strongly typed and also variadic. Okay, so anyway, that's what this says. This thing is a triple, and that triple is the triple that search takes as its single argument. Okay, so the other thing that we saw in that source sample was the parallel for, which deliberately looks a lot like a loop, but actually is a function, like a library function. So this is the signature, or this is an extracted version of the call from the source code. The first argument is a list of arguments, and the second is a loop body to run the arguments through. So this, I don't want to get into sort of type hieroglyphics here. This is the signature of the parallel for. So it's a lot like the functional map. The arguments are swapped to make it feel like a for loop, and it discards the results, but it works exactly the same way, except it's parallel. There is a serial version of it, but the important thing about doing control structures this way is, first of all, it adheres to sort of the Lego doctrine. You really can pull loop bodies out, and they're just functions, and you can bind them to variable names, and you can pass the name into the parallel for or whatever instead of an inline lambda. And all of that stuff works the way it should. The other thing is that you can make the familiar ones generalize to more powerful ones that turn out to be those sort of ferocious functional combinators that are generally avoided because they seem kind of esoteric or difficult. So we'll get to a couple of examples of that. This is just a little sort of flip book of like, here's the loop body looking like a loop body. It's really an inline lambda, so we've extracted it here into a bound variable, and we're passing the variable instead. This also is an opportunity to just show sort of a little piece of syntactic sugar. The reason function declarations look like they do in Mesh, like typical function declarations, is just because there's a teeny little, piece of desugaring that goes on, which turns it into a binding to a lambda. So all curly braces mean lambdas. All parens mean tuples. There's sort of a, truth in advertising in the syntax. I'm going to skip this for reasons of time, but I'll dig into it later. These are just the different syntactic forms of lambdas. Okay, so again, where was the transaction in that little piece of code? It was the single update statement. And as I sort of got ahead of myself, basically the fact that this is the only transactional operation and that it is a single assignment looking thing is key to understanding the feel of working this way and how sort of easy it is to achieve flow, so to speak, while doing it. So this is another thing that's happening in the image downloader. Basically, it just says when you click on an image on a thumbnail to get a full-size image, what actually happens is the client goes to Flickr and downloads a list of available sizes, and then the client figures out which one will fit in the window, and it asks for that one, it gets that one, and displays it. So it, again, is a multi-step conversation that's written in straight line, synchronous style. No callbacks, no sort of inside-out code. And the reason it can do it that way is because you've tucked it into its own task. And in fact, this spawn keyword here is, again, a combinator that just takes a lambda. So this thing is a lambda. You can do it like this if you want. Okay, so here's the spinner. This is not the most earth-shaking example, but I just like it because of what it signifies. This code, all this code does is it boxes up a double, and it starts a thread which pushes the double around a circle in a loop, in a loop with a sleep at the top. So somewhere in your program, there's a box with something tracing out the value of 0 to 2 pi over and over, and whenever anybody wants to draw a weight spinner, they just go find out what that angle is at that moment. So, in some sense, it reinforces this idea that things can be safe at a low level with no effort at all. But it also has kind of a nice feel to it. It just means that the live object idea can be applied in these places where, they can reduce the overall complexity of the program just by sort of exploiting this this idiom. Okay, so another combinator. This is intended to look like a while loop. It basically takes a predicate and a body lambda, and it does what a while loop does with it. The interesting thing about this is that there's a more general loop-like combinator that I'm calling cycle, for lack of a better term, which takes which is a generalization of that. Instead of just calling a loop body, passing nothing to it, and checking the predicate every time through, it starts like reduce with a initial value. The body is defined to take a value of that type, and the body is cycled on the value. So, it threads the value through repeated invocations of the body function. So that's useful. I mean, it's almost used more than the straight while loop version in the demo code. But the thing that ergonomically sort of matters to me about that is if you know how a while loop works, this other thing is one step away. It's really not a hard thing to get your head around. And you know, the fact that all of this kind of combinatorial power, which is more or less like that, is locked behind the wall of kind of obscure functional programming is, you know, it's not necessary. These things are close to each other, and all you need to do is sort of characterize the imperative stuff that everybody knows how to think in as kind of a Lego kit, and then the other Lego kind of starts to flow naturally. All right, so here's another demo. Let's see here. Okay, so what this thing does is it's like a billiard table, and you know, you can put a bunch of balls on it. They bounce against each other, and they bounce against the walls, and then you can, you know, you can sort of rubber band them by taking them out and then letting them come back in. And now it's not, I don't know if it's visible, but there's a up in the upper left here. There's a little heads up sort of printout, and it has a thread count. And so if I like sort of do the plus and minus keys, I can change the number of threads that are displayed there. And basically what's happening is, here, if I take it down to 1, you can sort of see what's, okay, so here the same thread is doing the display and the sort of game state updating. If it's 1, it does, you know, 1 thread for each, and so on. As the thread count goes up, I'm just parallelizing the sort of game state update, so collision detection and, you know, computation of new position and so on. Now, the thing that I intended to sort of demonstrate here is basically that, first of all, it works with a lot of objects, which, as an aside, I have to say, the mesh implementation over the JVM is only very lightly tuned. There's not much that I've done to make it fast. So the fact that this kind of thing runs as fast as it does is really impressive. I mean, each one of those balls is you know, like half a dozen. It's a record, which is like 2 object arrays, each of which is sort of half a dozen things. You know, strings and boxed objects. Every double in these demos is boxed. Every, you know, int is boxed. Everything is, you know, done in the simplest possible way. Just about the only thing that I've done to optimize actually is some of the stuff that Brian was talking about this morning, like hammering refs to lambdas down as far as they can go. So if they're like static instances of things that don't close over the environment, then I do that. But as far as data representation and, you know, tupling, the function calls that are tupled, those are real tuples. When you I mean, if you can't scatter them in a pretty straightforward number of steps, then they stay tupled. So that was the first thing, just as a test of scalability, of persistent data structures, and sort of being lazy about tuning things up for the JVM turned out reasonably well. The other thing was how to write the code in a way that let you be dynamic in your concurrency strategy at runtime. So that's what the up and down number of threads was. You basically parallelize the collision detection and the aging of the balls in a way that's sort of just parameterized by the library functions, and the structure of the code really doesn't change at all. So, quick rundown of what this thing does is, it's pretty obvious. The balls age, so that's one thing that's happening over time. The collision detection happens within the cells of this little checkerboard. When you partition the board into sections, you get contention, because some of the collision detection takes place across boundaries. So that's one place where the transactions get non-trivial in terms of the performance of the system. And it turns out that kind of contention, because everything is sort of very quick and snapshotty on these immutable data structures, that's pretty tractable. The other non-trivial transaction that happens in here is actually a little more interesting, even though the source of it is more prosaic. So when a ball is just moving in a straight line, it is owned by the square of the checkerboard that it lives in at any given moment, okay? And so you go into the transaction to update the state of this thing. Until you get in the transaction, you don't know where it is and you don't know what direction it's going and how fast. Now, each of those squares in the checkerboard is itself a mutable container. You know, it's a list of balls, basically. So you may be moving that ball, you may not be moving it at all, you may be moving it to anywhere in its neighborhood, and you don't know until you get into the transaction. So that's the kind of transaction that sort of steps over the line from being a straightforward, static, fixed set of things known at the beginning transaction to the kind of transaction where you don't know what you're going to need until you start the transaction. So that's the place where you go into the classic sort of coarse-grained, fine-grained concurrency problem, where, you know, if you want to simplify things, you just lock down everything you might need at the beginning, which means that you will be losing opportunities for concurrency that are actually there at runtime. If you want to get fancy, you only lock down what you know you need as you go, and that's when things get crazy and you have to sort of be very, very careful. The thing that transactions let you do, okay, and this source sort of just articulates the thing that I'm talking about right now. The thing that transactions let you do is effectively get the benefits of the fine-grained version without the very, very careful kind of trickiness of fine-grained locking. And the way you pay for that is retries. Like if you get down a path and all of a sudden it turns out that things are crossed up, then somebody can sort of blow up and try again. So this is where you need to be able to do that. You need to be able to retry. If you want to keep things tractable, even at the little places, you know, even if you assert that most transactions are really simple, once in a while you will get this kind of logic. And if you can retry, it's not a problem. All right. So this is another demo here. I can do this one really quick. Basically, this is a game of life, which is, I want to show you guys because it has a case where the transaction is sort of demanding in terms of scale, but not in terms of the dynamism that we just talked about. Right? So this thing is basically, you know, it's updating each cell based on its neighborhood. Okay, so check this out. I'm going to go to the flat one so it's easier to see. This game board is 256 by 256 right now. The filtering and state updating is happening with 4 threads, which can go up and down as with the other one. Now, I'm going to increase the game board size to a bigger size and to yet a bigger size, and then back down. All right, so whenever the game board changes, whenever the dimensions change, all sorts of pre-calculated stuff has to get recalculated. You know, it's stashing neighborhoods and so on, just sort of game state that's invariant with respect to the dimensions of the board. All of that stuff is happening in background and is getting swapped in all at once. While it's being calculated, the current game board is still going. And then when everything is ready, boom, the new stuff comes in. So, you know, this is while threads are updating in parallel, filtering is going on in parallel, tons of stuff is happening. But the coordination of those things is really simple. And so you basically can, you know, if you're in this sort of situation, the point is that the complexity that you add by parallelizing things and by taking advantage of situations where there's obvious benefits to concurrency doesn't interact with concurrency somewhere else. You don't have to say, well, if only I took out the game state reset or didn't recalculate or didn't use these pre-calcs, then I could use some concurrency here. There's no, that sort of entanglement doesn't really happen. All right, this is a, I don't know, I kind of like this. This is a wait notify that's done transactionally, so you don't have to sort of get your head around how the traditional wait notify works. All right. I'm going to wrap this up quick. Okay, one last thing here. The transaction that sort of is the workhorse of that game of life thing is an interesting beast because it is a fixed set of resources, but it's a non-trivial set. It basically, like, the transaction reads 3 things and writes 2 of them back. But because mesh has this sort of strongly typed setup, and because it can let structures be passed in that are variable, so it's polymorphic over width of structures, mesh can actually provide an API that lets you write transactions of this shape in a pure way. Let's see if I did the, no, okay. So assign there is the actual line of code from that demo that produces the change. So that triple in parens at the beginning is the inputs, and those are boxes with big lists in them, basically. Next is a pure function from values to values that does a fair amount of stuff, but it doesn't touch anything else by side effect. So it's purely functional, and what it kicks out is a pair of values that get written to the boxes specified. So in this case, the input and output test overlap, but they don't need to. And the type tracking of everything is done because the type system can say, you know, hey, that's a list of ints and a matrix of ints and a matrix of matrices of ints, and they're all boxed in the first argument, and then the parameter set of the second argument takes those things unboxed. So those sorts of correspondences are sort of trackable in the type system. And that basically speaks to the, that's part of the design philosophy here, which is types need to, like, pay their way. So a strong type system isn't its own reward. There's no particular reason to have one unless it helps. And the way it helps is by letting you tell the machine what you're doing. So this sort of enhancement, I think, pays its way because it lets you take something that was formerly inexpressible in the static type system. You know, I have particular types here, but there's going to be a varying number of them in the tuple I'm about to pass you, and express it in a way that the tool, any tool, an IDE, say, certainly the compiler itself, can exploit by telling you what's wrong with your code, by finding out that the thing that, you know, the int list you passed in to zip turns into like an int in every tuple in the list of tuples that it kicks out, and so on. So it's information richness is the reason why types exist. So this is Variadic signatures. Okay, I'm running a little late, so I think I have some stuff about transaction inevitability here, which is interesting, but I can cover that later in the workshop for people who are interested. All right, so thanks a lot.